Ladies and gentlemen, Dachahao. Hello everyone. Welcome to our first nexFrontier edition on digital fabrication, shaping the future of architecture. My name is Felix Mösner. I'm the CEO of SwissNex in China, the Science Consulate of Switzerland. SwissNex is here to show the best of Switzerland, build bridges and connect China and Switzerland in education, research and innovation. Situated in the middle of Europe, Switzerland is a landlocked country with no natural resources. This is why we have to continuously invest in brains, produce innovative solutions, and explore new frontiers, as we do today with nexFrontiers. Today we will learn about how digital fabrication opens a new frontier for a high-quality, future-oriented, large-scale architecture environment. Prominent speakers are from the National Center of Competence in Research for Digital Fabrication and Institute of Technology in Architecture at ETH Zurich, the College of Architecture and Urban Planning at Tongji University, and School of Architecture at Southeast University. This nexFrontier series is the newest webinar series at SwissNex in China, which spotlights cutting-edge research in Switzerland and in China, with a focus on Swiss National Centers of Competence in Research, NCCRs, and top-class research institutions in China. The aim is to spark potential exchanges and future collaborations. I would like to thank my team, Libing, Lefay, Sherry, and all the others for the excellent job during the past weeks. And now stay tuned for a very exciting exchange during these nexFrontiers. Libing, the floor is yours. Thank you.
Thank you, Felix, for your opening remarks. Today, we are very honored to have Swiss and Chinese experts from leading research institutes in digital fabrication to discuss how it transforms our way of design, construction, and building. Before we get started, I'd like to kindly remind our audience that if you have any questions during the presentations, please type them into the Q&A box in your Zoom control panel. We will answer them in the Q&A session. This webinar is being recorded and the recording will be available afterwards. Now I would like to introduce our first speaker, Professor Philip Block, Director of the Swiss National Center of Competence in Research in Digital Fabrication, full professor at the Institute of Technology in Architecture at ETH Zurich. He studied architecture and structural engineering at the Vrije University Brussels in Belgium and MIT in the United States, where he earned his PhD in 2009. Professor Block applies research into practice on the design, engineering, and construction of novel shell structures and has received numerous awards, including the Rossler Prize for the most promising young professor from ETH Zurich. Professor Block, the floor is yours.
Thank you, Libing, for the nice introduction. I will share my screen indeed. I think you need to stop unsharing for me to be able to, there we go. All right, so here we go. Thanks again for the invitation. I've been introduced, but I will start by talking a little bit about our national center, the NCCR Digital Fabrication, and then at the end I will give a few comments about our own research within this center. For me, and actually for the center as a whole, we are trying to make our contribution towards this gigantic challenge that by 2050 we are expected to have at least 2.1 billion more people on this planet. As Bill and Melinda Gates translated that challenge, what is needed is we need to build the equivalent of 1 New York City every month for the next 40 years. This is a huge, huge challenge, and particularly because our industry is unfortunately very bad for our planet. Globally, we're responsible to 40% of the global greenhouse gas emissions. We use natural resources in large amounts and very irresponsibly. We produce a lot of waste and then also we consume a lot of energy. These are simplified numbers, but it gives you a bit an idea of the massive scale and why it's important to innovate in the construction industry. So why it's important to get away of these outdated ways of construction and designing for them. So as a center, we believe that we need to change the ways we design, but also certainly build and realize our structural geometries. So zooming out, so national centers are national endeavors indeed that really want to promote long-term research with high risk and high return. Particularly the NCC Digital Fabrication is trying to really question and investigate to what extent computation, the integration of digital technologies can really disrupt architecture and construction indeed. We started in 2014. We work in phases. So currently we're finishing the second phase and are getting ready to start our third phase in 2022. So to go all the way to 2026. The leading house is ETH Zurich, but all key institutions and many of the universities of applied science in Switzerland are collaborating on this massive endeavor and challenge that we're facing. What's really nice about our NCCR is that we managed to gather experts in all fields that we consider key to tackle these challenges. So from architecture, civil engineering, computer science, mechanical engineering, material scientists, but also not unimportant socioeconomic, so sociologists, economists, and so on, to really understand the impact and the human dynamics behind all of these innovations. So when we say NCCR Digital Fabrication, then we are talking about over 140 very dedicated researchers that are trying to build better, design better through the means of computation and digital fabrication. So our headquarters is located on the Hunkerbeck campus at ETH Zurich. So in the back, you see the Lake of Zurich and downtown Zurich. So we are on the Science City on top of the hill in between the cows. There, more specifically, we're in the Institute of Technology. This is our building. It's called the Architect Lab, which has a quite unique roof. The roof is actually robotically assembled. It's actually a prime example of scaling up research. This is research by Gramazio Kohler, and there's many more research ideas in our building, in our lab. We actually are living in a lab. It's a living lab where we continuously experiment on ourselves and where we also do experiments downstairs in our large-scale robotic fabrication lab, where we have a state-of-the-art multi-robotic setup to do all kinds of prototyping. Indeed, to generate innovation and to question, for example, robotic additive manufacturing. You'll hear much more from this from Benjamin, of course, but also bringing robots on site and really questioning the relation between automation and human interventions. Again, a project from Benjamin. You will learn about this later, I'm sure, as well. New prefab, highly optimized new structural components, or even using things like sweaters, super lightweight formwork systems to realize efficient structural form. We have a focus on digital concrete, but we also are really looking into novel timber assemblies. This is by our colleagues at EPFL, at IBOA, where elegantly dry assembled timber constructions are brought together. Many of these things demand a lot of collaboration among disciplines, between industry and research and so on. And that is why the NCCR Digital Fabrication is also in parallel developing Compass, which is an open source computational framework for research and collaboration in the architecture, engineering, and construction industry. Compass is open source, is flexible, is modular, open. It's independent on any CAD software, and it offers basically extremely flexible ways of collaborating. The key idea why we developed Compass is because everyone seems to be reinventing the wheel to face the same challenges. So DRYO stands for don't repeat yourself or others. Learn from each other, share each other's work, collaborate, because the challenge for our industry, as I said, these 40%, or the 1 New York City per month, as Bill and Melinda Gates calculated for us, that is a huge challenge. So let's collaborate, let's work together. And so we're committed as an NCCR not only to bring new technologies, new methods, but also actually to offer these methods to the world and to engage with relevant industry indeed. I want to give you a very quick outlook of where the NCCR is going into its third phase. We have identified 4 grand challenges that we want to attack. One of them is digital timber. It's really bringing already a quite digitized industry, the timber industry, to the next level by basically augmented through interaction with robots on site to really provide modular, flexible software modules that allow also, for example, AR applications to enhance the crafts of the worker. The second grand challenge is digital concrete, where we continue our excellence of developing new 3D printing methods, new kind of very efficient, no waste fabrication, so formwork strategies, where we are pushing also how reinforcements and concrete goes together. So here we're really imagining to push the edge of what can be done in concrete indeed. The next grand challenge is we call digital construction site, where we want to look at the balance between full autonomous automation on site, capitalizing on large-scale robotics, on additive manufacturing, on cooperating walking robots, and so on and so on. Also drone concrete spraying and things like that. So we're really imagining the building site of the future where the human worker is enhanced to what it can do best, but where we also really are using technology to question what needs to happen off-site versus on-site and so on and so on. And then the last but not least, this is Grand Challenge 4. We are thinking about digital collaboration and basically how through Compass, but we can really learn from what we do, but also fully understand the socioeconomic kind of impact of all the technologies that are being introduced. So we are a large group of researchers that are keen to work with all of you. That's the Digital Fabrication NCCR. Now, maybe 2 minutes to give an insight on one project that we do as my own research group. We're trying to tackle the most wasteful structural element in construction, which is the floor. Did you know that in medium high rises of 15 to 30 stories that you see all over China, for example, 75% of these buildings, their weight is in the structure. And actually, if you zoom in, more than half of that weight is in the floors. So what we do is we bring back historical principles of compression to significantly reduce the mass, the volume needed. And these principles are not new. They come from historic structures. And that allows us, for example, in a 5 by 5 meter floor plate to only need 2 centimeters of unreinforced concrete placed exactly where it needs to be. And of course, this is where digital fabrication becomes extremely important, because in order to shape these non-standard structural geometries, we need to find new ways to fabricate them. For example, direct 3D printing, but in this case, this sand 3D printed floor serves as a large-scale prototype to show that with super weak, simple, low embodied energy, so low pollution materials, we can generate a floor that is structurally stable. And if you don't believe me, this is 1.5 tons of ETH nerds standing on a very thin 2 centimeter structure. The reason that we do that is indeed to reduce volume, but most importantly, to actually reduce the embodied carbon, to use as much recycled content and to be 100% recyclable at the end of life if you don't just reuse the building. So what is exciting here is that if you apply this to any of the medium high rises that you see around us, this would reduce the amount of concrete needed by 7,500 cubic meters for one building. Equivalently, this would mean that 1,200 concrete trucks less need to go to these building sites. So again, why we are excited about pushing these small innovations. What is more boring than just a floor that we all walk on? But if you know that all these floors together amount to more than 40% of the mass of the weight of these buildings, so 40% of the pollution of all these buildings, then I think it's worth really to question how we build and to introduce digital fabrication to do significantly better. So with that, my short introduction, I look forward to this discussion later, and thanks again for this opportunity.
Thank you, Professor Bloch, for the interesting talk. Now I'm delighted to introduce our second speaker, Professor Philip Yuan, Associate Dean of College of Architecture and Urban Planning at Tongji University, Director of Academic Committee of Shanghai Digital Fabrication Engineering Technology Center, Co-Chair of Digital Futures Association, founder of ArcUnion Architects and Fab Union Technology. Professor Yuan is also a member in the scientific committee of the International Association on Spatial Structures and the International Conference on 3D Printing and Transportation. His research mainly focuses on performance-based architectural tectonics, application of robotic fabrication equipment, and development of robotic fabrication technologies. Professor Yuan, the floor is yours.
Hello, can you hear me? Hi, thanks a lot for the kind invitation and the introduction. This is Philip Yuan from Shanghai. It's a great pleasure to be here with you today. Thanks a lot to Swiss Next China inviting me to be part of the event. And it's great to see my friends here as well, Philip Bloch and Professor Benjamin Dillenberg and Professor Hua Hao. I believe it will be an inspiring talk. Let's start off my presentation today. So Digital Future was launched in 2011 by me and Neil Leach, Professor Neil Leach, as a platform for the series of workshops, conferences, and exhibitions held at the College of Architecture and Urban Planning at Tongji University, Shanghai. For the past 10 years, Digital Futures has evolved from a local event to a global phenomenon. Each year, we operated a series of events, workshops, and conferences based on the annual theme. On the right of the page, you can see the list of the themes we have gone through over the past 10 years. So it is quite meaningful as I look back and review all the interesting topics we have been explored. And last year is a little special. Acadia Committee awarded our program as 2020 Innovative Academic Program Award of Excellence. It was also a great honor to be a member of our organizing team. Every year, we invited several important figures, contemporary philosophers, theorists, and practitioners to Shanghai. And the intention of the event is to form various discussions, conversations between the Western and the Eastern architects who come from different cultural backgrounds, and to reconstruct a new context for exploring the future of architecture. Even in those early days, however, Digital Futures has been highly aspirations. And the first conference, we invited Prize Prize winner Tong Man to give a keynote speech. And here is a very short studio to go through briefly and make an introduction of the history and the moments of our events. In the past 10 years, we have successfully invited a number of prominent educators from the leading schools of architecture and architecture associates to join and contribute in their series of events. Every summer, we had an exhibition proposed to showcase the outcomes of the workshops. So here is a glimpse of all the installations, artworks, experimental prototypes, and exciting projects which the Digital Futures series of the workshop has created. I think it's quite diverse and it's kind of dialogue cross-country, and also it's a very meaningful process for everyone to learning from each other. So it's quite cross-discipline, including the fashion design, material science research, computational design, and digital fabrication as well. So the Digital Futures has launched with a manifesto that calling the call upon the leading architects and architecture educators to give their time for the benefits of everyone across the globe. The response was astonishing. Educators from leading architecture schools in the world come together in a gesture of solidarity to offer students from all over the world, including those unable to afford the fees of the top schools of the architecture school, and the kind of educational experience that otherwise they could only have dreamed about. The initiative was highly significant for many reasons. Not only did it succeed in providing the online workshops could be as effective, if not more effective than face-to-face workshops, but it has also made a significant step in helping the breaking down the walls of classroom and to democratize teaching in different ways, especially in architecture education. So here you can see the statistics data of the number of applicants from the year from 2011 to the year 2020. It is obvious the Digital Futures had attracted progressively numbers of applicants throughout the world. Last year, the applicants reached its peak. Although they peer to the pandemic, it has been quite possible to conduct Zoom meetings, to use the contactless payment and to other groceries online. And the new situation joined people out of the familiar habits and forced them to adopt to a new digital lifestyle. And last year, it attracted 12,295 applicants from 33 countries and was followed by an offline audience over 500,000 viewers. The applicants coming from 71 countries, all continents, 1,057 institutions. Among the applicants, around 7,329 students attending the various workshops, and such as Tongji, UC Berkeley, UC Berkeley, UCL, RMIT, etc. And Digital Futures has an education platform linked universities and institutions around the world. The initiative has expanded its partnerships and maintained a long-term collaboration with a number of leading institutions, including the ETH Zurich, IAC, University of Stuttgart, Harvard, GSD, MIT, SciArc, RMIT, AA, UCL, and so on. So over the past few years, we have a lot of outcomes, including publications. And Digital Futures gradually grew in status. And a series of books was published as part of Digital Futures event, parallel with the event. We have been co-authored with Professor Neil Leach, Professor Aki Mangers, Professor Philip Rock, and this sequence of the books actually educate a generation. They can learn or engage into the computational design and robotic fabrication culture. The aim of the Digital Futures is to encourage international collaboration and interaction, and to promote theoretical scientific research into the computational design and the digital fabrication. The other areas of including some areas, including architecture intelligence. In 2017, an international PhD program was added and was taught by the leading figures such as Archimangus, Philip Bloch, Patrick Schumacher, Roland Snook, Mike Xie, Mark Burry, and others. We are currently preparing for a new website calling digitalfuture.org, which will come in this year. You can see maybe on the right side, which is going on right now. It would be covering all the contents of the events, workshops, and news of Digital Futures. More importantly, we aim to realize an online system and applications portal on the webpage for the global applicants to submit their applications. So this year, we will have 10 different hubs in 10 different countries, in different continents. So we're looking forward more people will engage into this global event. And last year, this future world broke through the walls of the classroom and opened up extraordinary, the new domain where education ideas could be disseminated for free to the students, even in the most economically underprivileged parts of the world, including Africa, including India, and so on. This year, we want to push these ideas even further. So education, we believe, should be understood as a universal human right and not a privilege of the few. So this year, the workshops will start on 26th June and end up with a hybrid exhibition on July the 3rd. And due to the continuous influence of COVID-19, international travels will be restricted. However, there is a possibility for Chinese students coming to Shanghai to join us in Tongji campus. Therefore, we would like to replicate the format of our last year workshop for the summer and planning a few hybrid workshops, integrate online instruction with fabrications in Shanghai, and we're proposing to have a lineup of physical installation in the end of the exhibition. So by the end of this presentation, I would like to show our 4 different research projects from my team, actually, that supported our research process. Since 2017, the pedestrian bridge has been our team's prototyping object, testing with different materials integrated with novel fabrication technologies. In 2017, we experimented 3D modified plastic printing technology, and that testing in our school from the ground floor to the basement, and which around 40 meter span, and the small village around 6 meter span. So which was totally by plastic printing. And it's around 1.5 tons and can stand 5 people on it. The second year is 2018. We try to wire arc additive manufacture technology with steel. Well, it's designed by different components and welding by the robotics, point by point. So this is the welding process by the machine. And also from 6 different parts, we assemble them on site. So second year, we can stand like 7 people on this 1,000 kilo bridge. And then times goes to 2019. It was our first time to try to attempting a hybrid approach, so which combining the metal 3D printing and the fiber filament winding technology as well. It's including the carbon fiber and glass fiber, which showcase the compression and tension, different kind of forces on the same bridge. So everything is done by the students. I think it's a learning process from the computational design and the robotic fabrication, and finally the assembly process. Okay, that's a brief, very brief introduction for the my team engaged in the last 3 years, and this is the last year actually, a little bit influenced by the COVID-19. We make a smaller bridge, which is 3D concrete printing. I think it's most of the students is online. Only 4 or 5 team members stay in the factory and working on this 3D printing process. But it's good test with the learning process to engage into the material performance and to learning how to generate different form by the different tools. So that is my speech. I'm looking forward for the discussion after the keynote speakers. Thanks a lot, and give the floor back to the to Libing.
Thank you, Professor Yuan, for the informative presentation. Now I'm glad to introduce our next speaker, Professor Benjamin Dillenberger, professor at the Institute of Technology in Architecture at ETH Zurich, principal investigator of NCCR digital fabrication. His research focuses on additive manufacturing and its potential to challenge traditional paradigm of design and construction. Professor Dillenberger's work was presented in Venice Architecture Biennale, London Design Week, and Art Basel, Miami. Recent work includes the development of a lightweight concrete slab as part of the DFAB house, which is a housing project entirely fabricated with robots and 3D printers. Professor Dillenberger, the floor is yours.
Thank you very much for the introduction, and it's an honor for me to speak in this round of friends and colleagues. Thank you for organizing the event, SwissNext. I will talk today about the core focus of our research, additive construction. Can you hear me, Libing? Is it? Okay. So what drives us? What is the background of our research? Huh? As Philip mentioned already in his previous talk, very nicely illustrated, we have to rethink the use of construction materials. We also should rethink the way we fabricate buildings, huh? Rethinking modes of prefabrication, modes of on-site fabrication to avoid a monotonous architecture that actually is not accepted by the population. Huh? And we should rethink building elements. Huh? Can we come out of the, what happens after the industrialized, standardized fabrication methods? How can digital fabrication methods influence our building elements? Huh? And we can take examples maybe on these highly optimized elements like we know from car industry. But of course, there's a big difference that cars are manufactured millions and millions of times in the same way. And the big challenge for us would be, can we manufacture buildings with the same precision, same optimization routines, but in a non-standard way? Huh? And can we use fabrication methods as we know from car industry, for example, robots, to bring to architecture in order to have an automated additive manufacturing method and in order to fully harvest the potential of completely digital manufacturing routines. And as Philip already mentioned, our research is hosted in the NCCR DFAB, the National Competence Center of Digital Fabrication. And our laboratory that we use mostly is the Robotic Fabrication Laboratory, actually a very large-scale 3D printer, one could say, with the ability to print with 4 different robots on the same part. So the research of my group focuses on large-scale additive manufacturing, related computational design work, and we focus on what we call element-oriented design research. So we want to really rethink building elements. And the motivation, and I will show in the next slides examples of these 4 different key aspects. Our motivation is to allow a higher degree of differentiation in architecture, to dematerialize architecture, so to use material more strategically, to increase the performance, also the operational energy performance of building components, and to make architecture with this higher amount of quality more affordable. And 3D printing is a very big family of manufacturing processes that all are based on material, energy, and information. And depending on the printing process, you introduce another kind of energy or another material. On the example of differentiation, I would like to show a work that we did for an exhibition in France. In architecture office and maybe in other disciplines, we know these small scale printers where the energy in this case is the temperature. We work also with very large scale printers like this binder jet printer, where the energy that is brought in is actually a chemical energy by a glue that binds loose sand together. What is spectacular of those printing processes that they already reach the architectural scale, 4 by 2 by 1 meter, printable within 48 hours in a high resolution, roughly 10 times, 100 times more than the screens we are looking at right now. So 40,000 by 60,000 pixel in every single layer can be manufactured, can be differentiated. So that allows us as architects to fabricate highly bespoke elements, highly differentiated, in this example on the outside with an ornamental structure, but also on the inside. So no single brick has to be the same. Walls, inner structures of these bricks can be totally adjusted to the specific load case and handling scenario. So using additive manufacturing in a robotic way means that complexity is not a challenge in architecture anymore, is out of the equation when it's about affordability of architecture. Fabricating simple rectangular boxes is not fast anymore than this intricate geometry that we exhibited in France. Secondly, I want to highlight the potential of additive manufacturing for the dematerialization. So here a student project where the ambition was to create an entire pavilion over 40 square meter of roof structure just by with a weight of 200 kilogram. And here you see as a reference 200 kilogram of building waste. So we use 3D printing in this case on another scale to print over 200 individual joint connections that are a mixture between nylon printed joints or these keystone, this key joint that is directly 3D printed in metal, which allowed us then to combine these highly sophisticated joint elements with bamboo as a lightweight building material and to create this large scale 200 kilogram heavy pavilion, light pavilion. Thinking of other lightweight structures, and Philip mentioned this already with the example of this lab, increasing the performance, making forms more specific to adjusting to a specific task, making them more lightweight often results in more complex geometry, like this lightweight bone structure of a bird, which would be very difficult to fabricate with traditional technologies. So in a prototype of a slab, we use 3D printing to create this topology optimized structure, where the computer helps us to take material out of the element where it's not needed anymore. Those are slow processes, and usually it's really difficult to fabricate those elements, and 3D printing might be really the key to introduce these kind of optimization routines in the design process. However, in order to allow a very direct design, we introduced a machine learning approach that allows the designer to directly play with these optimization routines. Here you see in real-time predictions of optimized structures with the help of machine learning to really allow an intuitive optimized design, which then can be sent to the 3D printer. And you see here a small scale 3D printer that would allow to print those elements within just a single hour. So in this example, we reduce over 80% of the material, and at the same time, we create voids of these lab elements, which would allow to integrate in a very compact way the infrastructure. And here, similar picture than what Philip showed, but with a smaller team. Now we would not fit anymore on this element, but you see that also this one can withstand a certain mass. Lastly, I want to talk about performance. So using digital fabrication methods does not always need to be mean reducing the cost, but could also mean we can increase the level of functionality, a higher degree of a higher value of each building elements. And the example of the smart slab in the DFAB house, we exactly tried that. So being able to design a prefabricated building system which would integrate many different functional layers, starting from integration of lighting, of course, material reduction, making it more compact in order to save floor or increase the floor height, usable floor height, and even integrating acoustic and optical structures on the structure. And we identified as actually formwork cost as the main cost driver of these complex building elements. And we used additive manufacturing in this case to really fabricate, actually 3D print the formwork, which was then combined with a high-performance concrete structure. So you see here an example of a digital formwork system consisting of many individual parts that can be brought together in a simple click and play system. And the structural assembly of these much more precise concrete elements that we know from compared to traditional ways of fabricating those elements. Combining it with another strategy to reduce material pre-stressing, which is facilitated by the introduction of even 3D printing adjustment details that allow a very precise pre-stressing. So you see here the slab that was then assembled with a precision of, I think, less than 2-3 millimeters on the seams and installed in a very short time on the construction site, helped us to reduce dramatic amount of material. And the conclusion of this project is that in this case, it is very strategically optimal to use 3D printing as formwork because we can combine it with also the high strength concrete. We can reuse the formwork as well. We tested that several times. But what's also important is to understand that 3D printing is a very new technology. So over the project developments of the projects that I showed, these methods already developed very fast and became now 4 times faster, 4 times cheaper to be applied in architecture. And I want to conclude with an image of the DFAB house, as mentioned already before, an iconic building that represents the potential of digital fabrication by using robots and 3D printers to be built. And lastly, I want to conclude with where I see the potential of additive manufacturing in architecture. So additive manufacturing could be the closest connection between design and its materialization. And we've seen that also in the examples that Philip Jan showed already. Additive manufacturing relates very well to construction because we ideally should see every single building as a prototype, and building elements are only required in small lot sizes. And differentiation and customization turn from a challenge to opportunity while using 3D printing. And 3D printing can play many various roles in architecture. I showed now an example of large-scale printed elements or small-scale joints. Further research is needed, and that relates very well also to the next conference topic that was announced, material intelligence. We need to learn to now manufacture more sustainable material systems. So, but showing these examples of bricks that have an unseen level of differentiation, reduce material use, connect sustainable material together, increase the building performance. I think it's an exciting time using additive manufacturing to rethink future bricks in architecture. Thank you very much. Looking forward for the discussion also.
Thank you, Professor Dillenberger, for the insightful talk. Now, please allow me to introduce Professor Hao Hua, Associate Professor in Architecture at Southeast University. He received doctoral degree from the Chair of Computer-Aided Architectural Design at ETH Zurich. Since 2014, he works at the Institute of Architectural Algorithms and Applications at Southeast University. His research focuses on computational design and digital fabrication. Professor Hua initiated javakuka.org for robotic programming. His works were showcased in international exhibition on architectural algorithms and applications, as well as China International Robot Show. Professor Hua, the floor is yours.
Good morning and good afternoon. I think I cannot start the video. Maybe Li Bing, maybe you can allow me to open the video.
Yeah.
Can you see my screen? Good morning and good afternoon, everyone. Thank you, Swiss Next, for this invitation. In fact, Southeastern University have been in collaboration with Professor Dillenburg since 2018. He frequently visited Nanjing to our Institute of Architectural Algorithms and Applications. Here the images show our design studio of digital fabrication of thin shells. The chair of digital building technologies and our institute organized workshops and lectures at Southeastern University. For example, we taught the summer school on generative design in 2018. Benjamin taught Python in Grasshopper. And in this semester, Benjamin and me are holding design studios on 3D printing architecture, which I will talk about in the end. Today, I will show our works on generative art. It's about transforming codes to graphics and geometry. Processing is a flexible software sketchbook and a language of coding for visual arts. We often use processing to explore design ideas. Both scientists and artists found their interests in generative art. As an architect, I would like to reveal its potential in design and digital fabrication. I organized the summer school every year at Southeast University. The students learned programming from scratch. After 2 weeks, they can program such fractals, L systems, or swarm. They also produce animations, which you may find on YouTube. Last summer, I discovered a t-shirt shop having such printer. So you can simply send an image to customize your own t-shirt. I let every student design and wear their own t-shirt. Each only costs about 70 RMB. Processing can simulate dynamical systems which develop such abstract line pattern. One student put such pattern onto a Chinese traditional fan. Such round fan only appears in costume drama, but the generative art may revive it into everyday life. And this project used processing to create sensational textures for planets in our solar system and apply them to the soft drinking bottles. So imagine if the bottle, the letters on the bottle and the liquid are dark, then you cannot see the letters until you drink up the bottle. I'm often amazed by the organic shapes in nature. They come in a great many varieties, but you can simply see the symmetry in them. To make a silhouette sculpture of jasmine, I tried to perceive the organic form from the machine perspective and from a human perspective. One can train a parametric model with observations. Here the images are the training examples from the a machine perspective. Once the parametric model is established, a designer can create compositions of them for the sculpture. Fitting data with polynomial is to approximate the data with linear combination of polynomials. To fit the jasmine petal better, we construct the Chebyshev polynomials in polar coordinate system. In the image on the right side, the green curves are fitted to the image beneath, which means, say, 30% of the first polynomial plus 60% of the second plus 10% of the third fit best to the image. The more polynomials you employ, the more precisely the curve fits the image. But from a human perspective, we prefer rough resemblance to precise fit. Equipped with a parametric organic shape, we create a program to generate many layouts for the silhouette sculpture. Actually, in some Chinese paintings, part of the object is outside the frame, so people can imagine what's outside the frame. So here we also implement such idea in our layout. And recently, we construct an unconventional pavilion in a traditional Chinese garden. The main structure is glued laminated timber and metal components made by laser cut and brass brake machine. We developed the textile reinforced plastic for the roof and make it semi-transparent. Once upon a time, hand knitting was very popular in China, but now people spend all their time on smartphones. We shift from hand knitting to CNC knitting machine so that one can digitally handle every yarn during the knitting process. Then the resin is sprayed onto the both sides of the fabric to make a thin shell. A cellular automaton is a collection of cells which evolves through a number of discrete time steps, according to a set of rules on neighboring cells. We let a cellular automaton run on the fan domain. The result is full of details, and every pixel corresponds to a single loop of knitting. Because of the loop is doubly curved, parallel streamlines cannot fit the entire domain. So we developed a computer program to find the places where you increase or decrease stitches. Finally, all textiles was fabricated in Shanghai. Then the 5 pieces of the roof are prefabricated in a local GRP factory. On the construction site, the timber frame and the roof were assembled respectively. Then the roof was lifted onto the timber structure to complete the pavilion. Under the pavilion, actually, you can see the sun through the roof because it's semi-transparent. Generative tool also help us to design timber structures. The famous bird puzzle has 6 wooden pieces sharing the same root. It inspires us to connect wooden pieces with bespoken joints. And crystallography, especially the Bava lattice, is very helpful to handle the symmetry in space frame. We choose rhombohedral to develop such timber structures. Although the bird puzzle hides the complex interlocking mechanism, here we use the shallow notches which inform the assembly. So any long combination will be easily identified. The shallow notches corresponds to the Boolean operations between the dimensional timber. So the robotic toolpath can be a function of the parameters in the Boolean operations. We developed we use the Java programming language to create the joint details, the instruction for the robots. The joint design improves the fabrication efficiency and simplifies the toolpath planning. The milling and the drilling volume is kept more minimum. So the final product is still similar to the raw dimensional timber. So the piece can be reused. The wooden pieces are connected by semi-rigid joints. So the structure is neither truss nor frame because there are bending moments. So it is definitely not a truss. And here a node unifies the displacements of multi-pieces as node, but they does not unify the rotations of the multiple pieces. So it's not a conventional space frame. And we use the direct stiffness method to analyze the structure, and it leads to undetermined system. And very recently, we find a systematic solution to this problem. And when architects design buildings, sometimes they learn from previous cases, and the generative design methods can help us to collect, analyze, and recombine previous cases. If you download models from the internet, the architecture model usually consists of triangular meshes, so there are no architecture information. So first we write a program to recognize the essential structures like floors and stairs. Then the computer can combine these structures to make a new design. Here, if you tell the computer to stack the floors vertically, then you get such design. Here is the skeleton, and this is the full building. Somehow it looks like designed by an architect, and you can specify more complex floor structures, and the computer will not fail you. Actually, the good thing about a computer is it can quickly generate thousands of solutions for you within a second. I think in this special case, the relationship between a computer and a designer should be reconsidered, because here the compute looks like they are creative based on the generative design method. And lastly, I should mention that Benjamin and me are holding a design studio of 3D printing architecture. For example, here in this group, they learn from Nervi's robot slam system. Here, the curved ribbon, the layout follows the stress lines in the slam. And now the students are making the prototypes. And also they have tried building these tubes, first printing the structure horizontally, then turn it 90 degrees and assemble it as a section of the continuous tube. Thank you very much. I think I will let the floor to Li Bing.
Thank you, Professor Hua, for the interesting presentation. Now let's come to the Q&A session. So we already received a lot of questions from our audience. So I will start with the earliest one. So with a very general question, maybe all of our speakers, you are kindly invited to provide your insights. So what's the biggest challenge or the key challenges of digital fabrication? Who would like to answer it first? Please turn on your microphone. Yeah. Who would like to answer that?
Go ahead, Philip. I would say.
Okay. So it's a pleasure to have this discussion, because it's really important, the representative group of people here, including Philip Block and Benjamin, and also Southeast University and Tongji University, actually the first, maybe the pioneer around the world to test different kind of technology in the past. Digital fabrication, I think firstly, we should engage into the industry, architecture industry right now globally, because of the carbon problem of the world, which Philip Block put forward at the very beginning of his lecture. I think it's meaningful to reduce the waste of material and save energy, make it high efficient structure in the future. That's the fundamental motivation for the optimization of the industry. So that's why digital fabrication can produce a very efficient, high efficient and save energy process to integrate a lot of computational design methodology and the new authorship, which based on the research of different groups around the world, and which can help us to reorganize our academic, reorganize our vision for the industry of the future. So digital fabrication is a platform, is an approach which can help us to go forward towards that special aim. So that is maybe a very easy answer. And secondly, I think because not just one group or two groups around the world, is a consortium actually, which already established by different universities in Europe, in the States, in Asia, and also in Australia as well. So all these vast universities set up their own labs, including NCCR, which is the most representative around the world, which gave us a demo that's actually the platform can help us to understand why digital fabrication can integrate not only the future, but also the past knowledge, which we developed in the last hundreds of years in architecture academic world. That's kind of a new integration which can link the past to the future. I think digital fabrication is not a totally 100% invention in our discipline, but it's kind of a more sustainable, it's kind of more adaptable approach, which can help the researchers and industry to go to a more meaningful future. So that's maybe a brief feedback from my perspective, and I'm looking forward, Philip and Benjamin, or how you can add on this topic. It's a huge topic. Hopefully you can answer it.
Thanks, Philip. So maybe going to the challenges that we are indeed facing. So the biggest challenges for digital fabrication, I see many. There is, I mean, it's clear why we want to do it, but placing, for example, material where it wants to be through digital fabrication, these forming strategies could be more expensive than the state of the art. And that's not surprising. We have a building industry that has been evolving for at least the last 50 years, if not the last 100 years, in a developing very simple systems that we all use all over, reinforced concrete, steel, and so on. So of course, now in the early, well, the initial scaling up of digital fabrication, it is hard to challenge these kind of well-established systems. So for me, actually, we can easily challenge them, but for that, we need to look at the bigger picture of a building. And so that is very hard to kind of convince clients and project teams to actually not just focus on that one complex element and raise flags and alarm bells and so on. So that is maybe another challenge that I see, is that because it's so unconventional, in a very kind of conservative industry, and it's conservative for a good reason, the margins are very small, there is not a lot of profit to be made, and we are playing also high risk in a sense that buildings need to be safe, and all of these things mean that if something new comes up, then people think that it will be not as well understood, so not as safe, but also significantly more expensive. And then last but not least, what I notice in digital fabrication is that it really kind of, it startles or it causes a shift in the entire typical process where everyone knows what to do. As soon as you introduce such a disruptive innovation, computational design, a digitally fabricated complex piece, then everything seems to be different. And indeed it is, because you need to organize the logistics differently. You need to organize who made the piece, who engineered the piece, who fabricated. So all these different kind of sequential processes that we have need to be rethought. And so I see these challenges, the cost, but again, I think there is a route there, because if we look at the cost in the bigger picture, then for sure we can compete. And more importantly, we need to put more value to what Philip earlier said. We need to put value to the impact, how sustainable is a solution, how little resources and so on. And these kind of things are currently not really being calculated fairly in the decision making. So I hope that many of the things that I now identified as big challenges, that they will become much more easier to deal with when we have clear guidelines, when we have clear expectations from clients to do better, and guidelines by governments to really require teams to be innovative and not just to build in the same outdated, polluting ways as the last 50 to 100 years. So a lot needs to happen, but I'm very positive because a lot of good things are also happening. We just need the will of the client. They need to ask for better solutions, and we need the governments to tell the designers, the builders, to not be as wasteful.
I can only second that. Of course, digital fabrication still faces academic challenges, research challenges, but I think the main challenge, because our ambition is to have an impact on industry, is really the structure of construction industry. As Philip mentioned, that might require a change of business models. if we compare, for example, research budgets of car industry, where they have multiple billions of dollars to investigate into new models, this is the construction industry is not structured in that way, that there is even this amount of research budget, for example, in the company. So it requires really a lot of, it requires another kind of qualification of construction people employed in construction industry, because these new ways of fabricating require other kinds of knowledge. And I think all the initiatives that were shown before are addressing this aspect, the conferences, the big teaching activities. And this is, I think, a very promising way. And then it's, we can face these challenges and also harvest the big opportunities that digital fabrication brings.
Maybe I have a few comments from the perspective of computational design, because digital fabrication is more or less related to parametric design. And actually, in my experience, for example, the students, when they are learning architectural design, so usually they want this shape, and they are not comfortable with there is a variety of shapes. Usually, I think it's a mind gap to shift from this shape to a family of shapes defined by computational methods. So actually, I think in the design phase of digital fabrication, I think it's very important to think geometry or think topology in a computational way. So it's not like the classical architecture. So say this shape is great, this building is designed by the masters. It's in the digital era, it's the knowledge and the technology and the efficiency, the performance, all these qualities are not combined with this shape, but the logic, the computational logic behind it. Yeah.
Thank you very much for your input. Then two very short specific questions to Professor Block. The first one is, which sectors or regions are most advanced in implementing these innovations, so these digital fabrication innovations? Then another one is, will future construction sites be more like a temporary assembly product line? If you could answer it. Yeah. Thank you.
Okay, so two interesting questions. I will try to be short, but they could open up an entire debate or conference even by themselves. So the first one about sections and regions, I think it's quite fitting that actually Switzerland is here talking to China, because I would highlight those two. And what is special about those two contexts is that in Switzerland, we are lucky to not be constrained by extremely tough regulations like in Germany and the EU and so on. And so that allows Benjamin and I to not experiment necessarily, but to kind of be able to find routes to introduce innovation into projects. So what I'm trying to say as an underlying kind of answer there is that it really depends on the regulations. And so regulations are not, in most parts of the world, are not open to allow people to really introduce into innovations. And again, in that sense, Switzerland is a nice testing ground, is a nice research lab for that. And then why do I say China? Is because I would say that people like Philippe Yuan and Arke Union and his team are actually world leading indeed in translating this directly into industry. And what I see as a huge opportunity there, and maybe the underlying kind of context there, is that I have witnessed that Chinese universities and China as a whole has a very interesting model to connect research with industry. And so also with these design institutes and so on, there is actually a structural opportunity for good ideas in research to find their way into practice very fast. And I think this is a very interesting, very important model that actually we in Europe, or in Switzerland more specifically, also can learn from. So you see that in both cases, my answer is, can we find a mechanism to avoid regulations that are just not allowing innovations. And so I see these two as very two cool mechanisms. And then to the question about, sorry, what was it? Temporary assembly line. Yes, I very much believe in this. More generally, what I think is very interesting is actually to just question the ratio between offsite and offsite and to try to find this balance. And so I cannot answer this question as yes or no, actually, because it heavily depends on the context. When you're building in a small town in Africa, or you're building for a large development in India, or you're building in a fast pace in China versus a very precise construction in Switzerland, it's totally different. But yes, I think we should challenge and rethink where fabrication happens. Right now, we have a lot of waste of resources, of efficiency, of time, and so on, because most of the construction happens on site. And I think we need to rethink this. And Benjamin gave some very compelling examples on how disruptive this could be if we rethink this. Sorry, I thought I could be shorter. This was a bit long.
Thank you very much for the answer. Then next question, I think it's for maybe Professor Yuan. Can you share some examples of industrial application implementation in construction area, especially in South China, of digital fabrication? Thank you.
Actually, really appreciate the comments, the talks from Philip Brock, because he mentioned it's really important to actually introduce develop research academic technology into the industry process. I think that is not easy. We need to understand the regulation. We need to understand the technology. We need to engage, integrate both of them. So they need some good, very important background. You should actually set up some common ground from the researchers and the practitioners. So that is here in China. I think university style is quite different to Europe because, for example, in Tongji we have a Tongji Design Institute. We have I have Archi Union Design Group. That is legally for the architects who can teach in the universities. I think the same in the States, but Europe actually is a totally different story. So the practitioners, you can, just like a doctor, if you don't know how to operate the patient, how could you be a doctor? So that's the same story. I think here in Tongji, actually, we have a strong support for the education, academic research, and that is actually a very important feedback from the scenarios and deployment of why we make research. So it's a little bit close or easy for us to translate this kind of new technology into the practice process. That is actually the methodology I actually deploy in the past 10 years. Actually, for example, both Philip Brock and me was invited to teach in MIT. Just half a year after our workshop, we construct the Red Pavilion in Zhejiang province. That is only 6 months. We construct an even bigger scale. We enlarge scale for like 5 times. And right now we try to enlarge it even bigger. So that is fundamentally is from our collaborative research. And also we try to challenge and set up our milestone in the academic world. What's our contribution to in this computational design robotic fabrication? But actually the scenarios in China is really helpful, even from the government. They give us a lot of encouragement. And the works for my team to do is try to make it legally, to persuade the experts, to persuade the government to passing through all the process from different experimental tests. I think although it talks easy, but actually it's really tough, really difficult. But I think the dreams for the tables here, the talkers, the speakers here is we try to make this kind of innovation that is not already exist in the industry, but that is something future for the industry. I think that should based on the test to failure, this kind of research and the practice process. I think it's very important to link the academic world to the practice process. So I think that is what we're trying to set up the platform, Digital Futures. That is a learning platform. At the same time, we want to produce our practice platform to all of my partners. I think that is really open future because the industry is huge. And the market is huge, but the technology is most important. The future knowledge is most meaningful. That is based on this kind of public platform and collaborative platform. So thanks a lot for the question.
Thank you, Professor Yuan. Then the next question is for Professor Dylan Berger. Can you please explain more about using machine learning in topology optimization of the structure? Thank you.
Yeah, it's a nice question. Maybe the bigger picture behind this, and I think Professor Hoa already addressed it as well, that there's a link, of course, between using the computer in the design process and using the computer to control machines to fabricate. And I think the biggest potential of digitization and architecture is when both things go hand in hand, that when the fabrication information can be integrated into a design software, then maybe other performative criteria can be integrated into the design process. And then, of course, we can use robots and 3D printers and other machines to then manufacture. And the example, and I just showed it to give one example, is that having the ability to construct new forms, to optimize them, to differentiate these forms, might require also new design instruments. And especially for architects, it is quite relevant to have an intuitive, very direct feedback between, for example, structural analytics or also other criteria that can be then integrated into the design process. So I would see for example, machine learning in relation to topology optimization. In this case, it was used to it is not a very precise analyze or optimization result that you get, but you as a designer can use artificial intelligence in order to more intuitively design.
Thank you very much.
But there could be other, maybe just there could be, of course, other roles of machine learning in the design process as well.
Thank you for the input. Then the next question for Professor Hao Hua. So it seems that learning how to do algorithms and 3D printing are a must skill to create generative art. So what are other skills or techniques that one needs to master? And are there any challenges or obstacles that you have encountered in your projects? Thank you. Actually, there are a lot of questions, so we have to limit a little bit the amount. So I just pick up maybe the most important ones. And it would be great if you can give some short answers, if possible. Thank you.
I think if you wanted to start doing generative design in 1 week, I think you just use processing. I think it's very friendly. The processing, the software is designed for artists or the designers and for architects. But if you are thinking about what is generative art, I think it's about many things. Actually, here in China, it's very interesting. Like 10 years old students, they already learn programming, but by these visual programming tools, you link between components and you can do some interesting program. I think the future here, the reality is different from my generation. I think now the kids can be very playful with these digital tools. I think, but I think they didn't connect doing art and programming. If they connect the two things, I think it will be very interesting. Yeah, thank you for the question.
Thank you. Then I have a very latest question. I think it's very interesting. Well, renovation is becoming a domain topic nowadays. In terms of both structure and tectonic, is digital fabrication a possible solution, like partial renovation of a building? Thank you. Who would like to go first?
And actually, my team is doing a lot of renovation work. I think the digital fabrication scenarios is not 100% totally use robotics process. Actually, digital fabrication is a very large framework, including different kind of materials, different kind of craftsmanship. And the renovation could be one of the most important scenarios because every renovation project have this customized objects we need to produce and to fit to the original building. And the digital fabrication is very efficiently, you can use the 3D scanning and the modeling process and 3D printing technology to implement all these new technologies and engage them into the renovation project. So actually we have several projects which is already finished constructed and some of them under construction, but most of them I try to produce a ratio of digital fabrication, that the ratio of robotics from 15% to 75% in different projects. Actually, that is the revolution which is really happening. That is not a black and white process. That's actually the black, gray, and the white process, actually, which we need maybe like 50 years to passing through all the process to a digital future.
Thank you. Then any practice to be shared from a Swiss perspective?
Not directly a practice one, but we have a new colleague in our institute, Silke Langenberg, who actually demonstrate indeed the value of digital fabrication in doing respectful renovations, where basically you find a balance between, for example, it's an example, right? Between an aesthetic continuity, but nonetheless not trying to mimic or replace, but really clearly introduce an alien part so that future restorations, renovations, people can recognize it as a novel addition, but that it's not kind of being confrontational. In the NCCR, we are also looking at renovation now in the third phase and restoration more specifically. Because also you can imagine that one can set the boundary conditions differently, and we can try to low impact, lightweight solutions that perturb the heritage project as little as possible, and that just do a very punctual, very custom, very precise kind of intervention. And that is, of course, exactly where digital fabrication has a lot of opportunity and outlook. So unfortunately, no practical hard facts yet, but we see a lot of potential indeed. Yeah.
Thank you. Yeah, let's move on to the next question. Is it possible to upscale this technology to city level for new urban construction, especially for developing countries, as the second wave of urbanization will take place mostly in Asia and Africa? And how to measure the environmental impact of digital fabrication comparing with traditional construction ways to achieve truly sustainability?
Sorry, there I want to directly jump in, because that is exactly why I showed digital fabrication applied to a standard element, right? To a floor plate and so on. And it's also related to the comment or the answer of Philippe Yuan earlier, is that it's not black and white. So when you see many of our projects, you see very fancy, flashy kind of examples, but we do them to really push ourselves. There we're trying to change and to question everything. But if you then break down our projects and identify specific kind of incremental steps to common practice, then yes, we can have a big impact. And so, for example, I presented with the floors. We can save, if we introduce these floors, we can save 1,200 concrete trucks going to one building less. So, and these geometries can only be introduced if you have a smart way to fabricate them. They're non-standard, so they demand non-standard solutions, meaning digital fabrication. So yes, I very much believe that many of the things that we showed in different kind of degrees will be essential to shape our future cities in the most sustainable way possible.
Thank you.
Yes, totally agree. And actually, we have another professor representative in China whose name is Professor Xu Weiguo. Actually, their team from Tsinghua already doing some on-site institute robotics right now, which is one project constructed 3D concrete printing in Shenzhen. They start yesterday. I think it's like a swarm robotics, which can printing a garden, a concrete garden inside an exhibition center. That's a showcase for the future 3D concrete printing can not only print like a single object, but also it can print like a city. That is, I think the Institute Robotic 3D printing is really meaningful for our future, not only on the 1 floor or 2 floor buildings, but also if we put them in the high-rise constructing machine and the 3D printing technology, if we collaborate with this kind of different scenarios, which will absolutely printing the future. Not only in China, but also maybe in India, Africa, this kind of developing countries. That is really meaningful because this kind of low budget projects, just based on different kind of very typical or copyable platforms, and people can learning really fast, especially in different kind of housing project. Which is really very interesting, and I'm looking forward that the digital futures in robotics not only serving for some custom high-end project, but also for some low-income people around the world.
Thank you. Another specific question. Do you think the robots we have borrowed from other industries can actually automate the construction process, or we have to develop specific robots as well? Maybe Professor Dielenberger?
Yeah, I can give my opinion there. It's also related a bit to the previous questions, and I think related to also the talks we've seen. So it's of course, construction industry is a very differentiated, diverse industry, and already now we see many different machines on construction sites, many different ways how to construct a building. There are local differences, there are differences from building to building, and I think it will be a mix. Huh? So there are generic machines like robotic arms that are able to fulfill already a broad range of tasks, but nothing speaks against having an optimal robotic setup that is really designed for a specific purpose. Huh? We do have sometimes machines that more or less mimic what would be a manual process. Like there are robots that do milling, and we have other ways to mill by hand, for example. But there are also other processes. I would count, for example, also high resolution 3D printers into the family of robots, and there's no precedence, and they work with the main intelligence which is in the print head. So the scope will be wide, and I don't think that a single family of robots, neither existing ones or specifically designed, can be the total answer to the challenges.
Thank you. Well, I think I will have one last question. So for people who are already working in the architecture firm, so the architects nowadays, what should they prepare themselves for this digital future, for this future of architecture? Maybe 1 or 2 sentences, some short suggestions from each speaker to end this webinar, please.
I can maybe I would start. So it's a very exciting time because there's this disruptive moment of digitalization entering construction industry. So architects and everyone involved in the construction industry should be open for these changes, be able to critically reflect also how these changes could have a positive impact on architecture.
Thank you. Professor Yuan?
Yeah, I think it's great to make some comments because all the architects and the structural engineers, it's a daily, it's a whole life learning process for you. It's not all the knowledge from the school, but actually that's why we set up Digital Future as a learning platform. Actually, you can learning not only from your school, and you can learning from the world, the most important figures around the world. So I really appreciate Philip Block set up Compass in ETH, and also we We want to set up more like a sharing culture inside our discipline. So we should learning through our life, and we should learning from the world. So that is, I think, the next generation, because the knowledge is growing. We should keep learning.
Thank you, Professor Yuan.
I would, it's not specifically on digital fabrication, but I would like to ask all our colleagues, both architects and engineers, to inform, or to first to get informed, and then to inform our clients on how much impact buildings have. And by doing so, then to be looking openly to all options that there are to do better. And then we will naturally see that not in all contexts, not in all situations, but that digital fabrication and rethinking on also how we design can have a meaningful place in modern practice. So I would say actually just be more aware as designer of what impact you have. And then you will naturally have to be curious and find solutions. And that would be my advice or my comment.
Thank you. Professor Hua?
I think for some architects, digital tool or digital fabrication sounds like a challenge to them. But I think architects don't need to do it directly. I think it's nice to think about what is the difference between the digital era and this classical era. Actually, in the history of architecture, there are important movements like the postmodernism or the Peter Eisenman's approach. I think they make an interesting difference to the conventional design theory. I think for the architects, I think it's very interesting to think about now what's the difference between the digital era and this classical modernism. I think maybe based on this question, interesting results will come out.
Yeah,
thank you.
Thank you very much. Well, due to time constraints, we will have to end the Q&A session. So thank you very much. A great appreciation to Professor Block, Professor Yuan, Professor Dillenberger, and Professor Hua for your insightful presentation, and also the dynamic exchange and discussion. Now, to our audience, if you have more questions, please send them to the email address on this slide. We will forward the questions to our speakers and give their feedback to you. You are also more than welcome to scan the QR code to follow us on our social media channel or subscribe to our newsletter. Thank you indeed for your active participation, and we look forward to meeting you in our next events. Thank you. Bye.
Thanks, everyone. Bye.
Thank you, Libby. Thank you, everyone.
Ciao, ciao.
Bye.
哦，好像已经走了，来不及了。